Hello there, my name is Peter White, and I'm a quantitative software engineer with Engine, and I'm here today to tell you why now is the time for machine learning in finance. And now is the time. Whatever your preconceived notions are of machine learning, it really boils down to this. Software that is able to learn and improve on its own is a clear step forward in technology, and like we've seen many times before, to ignore that is asking for trouble. I think we all remember Blockbuster Video. Remember when Netflix used to be a physical place? You'd have to actually drive to the store to get a movie. It seems almost barbaric now, but at the time it was the greatest. I personally loved Blockbuster. I felt so much more invested in the movie. I don't think I've ever seen the end of a movie on Netflix, but Blockbuster, that was your night. And it wasn't just me. In the 90s and early 2000s, Blockbuster was huge. At their peak, they were making over $6 billion a year. They had over 50,000 stores. All that without even renting adult videos. Do you realize how insane that is? Most video rental stores only stayed open because they had a steady supply of creeps looking for smut. Blockbuster said, we don't need them. And they didn't. $6 billion a year. 50,000 stores. So where are they now? There's only one left. In Bend, Oregon. That's a sad way for a multi-billion-dollar corporation to end, dying alone in Bend, Oregon. So what happened? It's easy to just say Netflix and be done with it, but there's more to it than that. The real death of Blockbuster was the refusal to embrace a clearly superior technology. When Netflix first started, it's not like they were some crazy, destined-to-succeed company. They were a mail-order DVD rental business. You would send them a message, they would mail you a video, you would watch it, and then mail it back. The whole thing took days. It wasn't a great business idea. Nobody was sitting at home going, man, I'd really like to watch Batman in 3 to 5 business days. I hope someone can mail it to me. So you can forgive Blockbuster for not being super worried right at the gate. But still, the idea of delivering a movie directly to the person's house is clearly superior. Blockbuster knew as well as anybody that most people in North America are fat and lazy like me. We want the fun thing brought directly to us. I don't want to have to go out to get it. I don't have to put on pants and leave my house. Bring it directly to me. Put it in my face. So you'd think when video streaming was first introduced, Blockbuster would be all over it. But they weren't. They passed on it. I guess I get it, because when video streaming first started, like we all know, the quality wasn't great. It was choppy, it was unreliable. If you didn't have a great internet connection, you couldn't even try to use it. So Blockbuster looked at that and thought, why would anybody want to waste their time with this when they can simply drive to the store and get a great quality DVD? And obviously they were way off. Everyone wanted video streaming, and as it got better and better, Blockbuster fell behind, and then it was too late. And I think a lot of people are sleeping on machine learning the same way Blockbuster slept on video streaming. I know a lot of people are already using sophisticated methods and algorithms and programs to help with their decisions, and machine learning is the next step. Those methods currently in use are like mailing DVDs. Machine learning is streaming right to your house. Look outside of finance. Machine learning systems are already excelling at a lot of things. It's been over 20 years since the best humans could beat computers at chess. Machine learning systems are better than the best humans at Go, which the nerd clan tells me is very impressive. They're better than humans at poker, at video games, at programming, at diagnosing diseases. They're even better than us at abstract things like reading comprehension and love. Do you really want to bet on them never excelling at investing? If machine learning systems could process all the information needed to make these decisions with investing, there's no reason they couldn't be as good. Because at the end of the day, it's really about having all the information. Look at coin tosses. They appear random, we treat them like they're random, but a coin toss just follows the laws of Newtonian physics. If we knew everything about the system, we could model it pretty well. If we knew how much energy went into the coin toss, the coin's trajectory, its angular momentum, the humidity of the room, the current phase of Mercury, which Ryan the Flipper found hotter, etc., we should be able to predict the outcome. So, how does this relate to finance? Well, in 2017, there's a great paper published on replicating previously found anomalies or variables that seem to lead to excess returns. And they didn't just cover a couple dozen variables from other studies. They covered 447 different variables that had previously been shown to be informative. And there are definitely more than that. And while some variables may be more or less informative, there's a lot of information that can be used to model a stock's return. And we haven't even begun to talk about alternative data. The more information about the system we incorporate into the model, the better the model should perform, in theory. And some quants have tried that. Throw as many variables as they can think of into a linear regression and see what it spits out. But that's not how linear regressions work. That's like putting all the things that taste sweet into a cake mix. It's great in theory, but there are some issues. These models don't work because this approach violates a core assumption of linear regressions, and linear models are not capable of capturing the complex relationships that will exist between the input variables themselves and between the input variables and the desired output. A core assumption of linear regressions is that all of the input variables must be independent of each other. With a large number of variables, this becomes very unlikely, and the results can become nonsensical. For example, the number of rooms in a house tends to be well correlated with the size of a house. If you put the size of a house and the number of rooms into the same regression, the linear regression can't distinguish the effect of one input over the other, so you might get that their effects are opposite signs, even though you would expect them to have the same sign. Okay, so you're thinking that's fine. I'll keep the inputs simple, I'll use 6 factors that are independent of each other, and use a single variable to represent each factor. The linear regression is still too limited because, well, it's linear. As a general rule, straight lines don't exist in nature. Linear models have several weaknesses, even when used correctly. First of all, it's a constant proportional relationship. I mean, let's say you like PE ratios, and lower is better. Do you care if a stock's PE goes from 100 to 95? Probably not so much. Would you care if it went from 15 to 10? Probably a bit more. What about if it goes from 10 to 5? I mean, now it's starting to smell like a value trap. But a linear model would say the change in 5 is just as good in any case. You can't have a Goldilocks zone. And linear models also don't care where you're at in the number line. If you followed a linear model and believe a lower PE is always better, then your model would tell you that the best investment possible would have a PE of negative infinity. That's a poor representation of reality. Linear models are also very limited when capturing the effects across input variables. What if higher PE ratios are supported by, for example, higher EPS growth? Linear models can't capture combinations of variables at certain values that might work well together. Here's a simple example of a nonlinear model that captures a variety of scenarios. As we can see here, lower isn't always better, and higher isn't always worse, and we can combine different combinations of different variables at different values. Linear models simply cannot do this. This is an example of a decision tree, and they're pretty easy to understand and follow. We start at the top, and in this case we think PE is the most important feature. If PE is less than 15, we go to the left. If it's greater, we go to the right. If we go to the left, momentum is the next most important feature. If it's negative, we go to the left, and if it's positive, we go to the right, and that brings us to the output of the model. It's pretty clear how we get from the inputs to the outputs, right? The use of nonlinear models removes the constraints that linear regression put upon us. Alright, we've been beating around the bush about it for a little bit. What is machine learning? If you Google it, you'll find something like this. Machine learning is an application of artificial intelligence, AI, that provides systems the ability to automatically learn and improve from experience without being explicitly programmed. Now that's a pretty vague, not super helpful definition, which is probably why there's a lot of misunderstandings around machine learning. It's hard to describe it exactly. I know I first heard about it the same way most of you probably did, watching Terminator 2. I remember I was 13, and that was the greatest movie I had ever seen in my life. There's robots and time travel and Skynet. I thought Skynet was the coolest thing in the world. I never would have dreamed back then that when I grew up, I'd actually be working on AI systems. And let me tell you, if me as a child could see the kind of stuff I'm working on now, he would be very disappointed. I haven't seen a single cyborg since I started. It's all just nerds writing computer code. But I have a better understanding about why the definition is so vague now. Machine learning is a vague definition because it has to be. It's not an easy to nail down specific thing. It's a broad term for any system that automatically learns from data. It's vague because it's an idea. It's a concept. It's almost like how calculus is a tool to solve math problems, machine learning is a tool to solve prediction or classification problems. Although there are a lot of ways to use machine learning, all methods are, from a high level, reasonably similar. The goal is to look at as much labeled data as possible and formulate the best possible model about how our inputs relate to our outputs. The model is a description of how the variables work together to reach the output. You can then use this model on new data to make new predictions. The model is created by following an algorithm. A machine learning algorithm is a mathematical procedure that sorts your data. There's a number of different algorithms that can be used, but again, they all do the same thing. They're looking for patterns in the data that model the relationships of the inputs and the outputs. Now, you might think that more traditional linear regression models can do the same thing, and in a way you're right. They do the same thing in the same way that a kite and a plane can both fly. Sure, they're both in the air, but one is a hell of a lot more impressive than the other. I mean, regression is neat, but the difference with machine learning models is that they can coax out far more sophisticated patterns and trends than regression could ever dream of. Machine learning is like the next step in evolution to regression. Now, regardless of the sophistication of your algorithm, a machine learning model can only ever be as good as the data that it's given. If there's errors in the data, there's going to be errors in your model, and there's going to be errors in your prediction. That's just how it works. It's built 100% off the model, so whatever you give it is what you're going to get out. Like for instance, in 2016, Microsoft created a machine learning Twitter account that would read people's tweets and then learn how to tweet based on that, which sounds like a really cute idea, but less than a day later, that thing was horribly racist. If you put racist data in, you're going to get a racist model out. That's just how machine learning works. You have to be incredibly careful with your data. As with many things, particularly with machine learning, a little bit of knowledge can be a dangerous thing. ML is still a relatively young field, and online programs are cranking out quote-unquote data scientists. So it's important to recognize and address some legitimate concerns about ML. The most common concerns, especially in finance, are overfitting, data mining, and black boxes. So what do these buzzwordy sounding things actually mean to people in finance, and how do we address them? Overfitting is when you select a model because it did really well on some set of data, but really poorly on another set, even though the data are kinda similar. Quants can be guilty of two kinds of overfitting: overfitting the data and overfitting a backtest. Overfitting the data means the model is basically memorizing every example instead of generalizing. The model knows the data it was trained on so well that once it sees something that's just a little bit different, it cannot handle it and your predictions are garbage. Overfitting a backtest is pretty easy. Backtesting is a way to theoretically see how an investment strategy would have performed over some time period. If you do enough tests on enough different variables, you'll eventually find a strategy that just happened to have a good run during that one time period. This type of multiple testing is a cardinal sin. For instance, if you use the number of coffees sold at Tim Hortons in Waterloo, and the number of hockey teams Jim Balsillie was interested in buying between 2000 and 2010, it just happens that you would have had a perfect buy and sell signals for research and motion, and you would have made a killing. But this strategy wouldn't be very good at any other time. All of this overfitting leads to an all too familiar story. We're presented with a model that we're told is amazing and has great backtest results, but then we start using it and it underperforms. So when making forecasts or predictions, we care about how well the model does when given data the model has never seen before. So it's common practice to have a holdout period to test the model on. But if you only have one test period, it's pretty easy to test until you have a model that does well in that one test period. The more test periods you have, the harder it is to find something that consistently works. To avoid overfitting, we go above and beyond standard testing by employing a new technique called combinatorial cross-validation. We divide the data into a number of groups and use literally every combination of data groups to form test sets, and we get a much larger sample of tests to ensure our results are robust across many unseen scenarios. We can also use the combinatorial cross-validation approach when backtesting to generate a large number of scenarios that are based on history but haven't actually happened before. If we treat backtesting more like a risk management tool, we can create a distribution of how well the model might perform in different scenarios. By using all combinations of test sets, we could have a scenario like the dot-com bubble and the housing crash back to back. That way we can get a much better sense of the robustness of the performance, even in extreme stress periods. Data mining is a little bit like finding the guy on the right and thinking you found Arnold Schwarzenegger. Sure, it might look right, but something is a little bit off. One of the causes of overfitting can be data mining. But more importantly, data mining can come up with some pretty ridiculous explanations. Data mining is often thought of as getting as much data as you can and finding what has the highest correlation with whatever you're interested in. It's a common temptation to throw everything into the algorithm and let it sort it all out and find relationships. But the big concern is finding spurious relationships. When comparing so many variables, you're bound to find things that are correlated by coincidence but don't have a true relationship between them. In a paper literally called Stupid Data Miner Tricks Overfitting the S&P 500, they found they could do a linear regression of the S&P 500 against butter production in Bangladesh over a 12-year period and get an R-squared of 75%. That's amazing. If they added cheese production in the US and the total sheep population in Bangladesh and the US, they got an R-squared of 99%. Problem solved. Quants should just go back to being physicists. Avoiding data mining involves a lot of careful planning. A lot of research has gone on to find informative variables in finance, and that's where we start to ensure there's a reasonable grounds for the inclusion of a variable. Then we go through a robust feature selection procedure. We use a new technique called mean decrease accuracy that systematically tests how each feature affects the performance of the model. When we combine this with combinatorial cross-validation, we are able to ensure that the features we've selected are truly important. This approach is as close to a controlled experiment as we can get in order to get enough confidence that the features we've selected are significant, and we found robust causal relationships between our input variables and the output. One of the biggest concerns about machine learning models is that they are black box systems that generate predictions for unknown reasons. And this is an understandable concern. If you're not careful, these issues can crop up. For instance, there's kind of a half-famous example of someone who created a model that was supposed to tell the difference between a picture of a wolf and a husky. And they made the model look great through the training, perform great in their testing, then they put it loose on real-world data, and it kind of stunk. And nobody could figure out why until it was discovered that the way it told the difference between the pictures was whether or not there was snow in the background. If there was snow, it was a wolf. If there was no snow, it was a husky. That's a pretty garbage model. And people like to point at that and go, see, machine learning is stupid. It doesn't even know why it's making the answers. And I remember the first time I heard that, it shook me a bit. I was like, oh, I should look into this. And I did. Two things. One, that was a few years ago. Their technology has improved substantially since then. And second, and more importantly, a student built that model in, quote, a couple of hours. Of course it was awful. I built a robot in undergrad that was supposed to solve a maze. All it did was spin in a circle and catch on fire. You can't use that as an argument against machine learning. Yes, you have to be careful when creating your model, but in the hands of a professional, these situations are completely avoidable. We have a glut of tools at our disposal that we can use to analyze our inputs and outputs to completely understand what's going on with our model. And the beauty of these tools is that many of them are model agnostic, which means we don't even have to know how the model was created to be able to understand it fully. This is handy because the inner workings of a machine learning model can be a bit complicated, and it can seem difficult to understand exactly what's happening at every intermediary step. But the beautiful thing is, in order to understand how your system works, you don't need to know every single detail. I mean, think of it like baking a cake. You don't need to understand the chemical reactions going inside your oven to understand what's going on with your cake. You can simply examine the cake and the ingredients and figure out what happened. If your cake is salty, you probably use salt instead of sugar. If it's burnt, your oven was too hot. It's not necessary to understand each intermediary step to understand what's happening. In fact, check out our blog for an in-depth look at some of these wonderful new machine learning interpretability tools that are now available. As machine learning continues to advance and improve, it's hard to imagine that at some point it doesn't surpass, or at very least compete with, current investment strategies. I believe that point is now. More and more nerds like us are working on this every day, and with advancements in software libraries and data availability, machine learning models are getting more and more powerful by the day. Plus, huge firms are throwing an insane amount of money at these things, which is speeding up development immensely. Like it or not, machine learning models are most likely the future of finance. Being able to properly use, understand, and explain these models is going to be an essential skill moving forward. I know many of you have preconceived notions about machine learning, but it's time to accept the fact that machine learning systems are here to stay. They're powerful, they can find the kind of patterns and relationship that other systems simply can't do. They're robust, they can handle all kinds of different data, they're flexible, they're able to use different alternative data, and most importantly, they're interpretable. We're able to understand these models like never before. And listen, I don't want to sound like I'm some sort of high school football coach that's just here to rile you up about machine learning. I just want to emphasize that once this hits a critical mass, it's going to be too late. We talked about Blockbuster at the start of this, and how they got decimated by not being open to new technology. But the truth is, they really weren't that far behind. Netflix started video streaming in 2007, and within 4 years, Blockbuster had its own streaming service up and running. But despite having infinitely more resources, infinitely more experience, and infinitely more influence, it only took 4 years to be so far behind that they could never catch up. If you look outside finance, it's obvious that the machine learning revolution is here. AI systems are in place all over the world. They're doing everything from suggesting you movies, to driving your cars, to diagnosing your illnesses. Machine learning models are adaptable, interpretable, flexible systems that can help with almost anything, and finance is no different. The only way to get an edge in investing is to stay ahead of everyone else, and you don't want to be behind on this one. Remember, technology improves at an alarming rate. When the tipping point comes, it comes quick. And you're either going to be Netflix or you're going to be Blockbuster.